Most developers start their journey by learning how to write code that works. You build functions, connect databases, and create interfaces, celebrating every time your application responds correctly to a click or request. But as your systems grow, you quickly realize that correctness alone isn't enough. What works for 10 users might collapse under 10,000. A perfectly coded API can become unreliable if a dependency fails, and a fast database today can be tomorrow's bottleneck. This is where software architecture steps in, transforming your approach from just making things work to building systems that are fast, reliable, scalable, and maintainable. Let's explore the 12 essential architecture concepts every developer should know. Software architecture isn't about drawing fancy diagrams. It's about understanding the patterns that keep systems running smoothly under pressure. The 12 foundational concepts: load balancing, caching, content delivery networks, message queues, publish subscribe systems, API gateways, circuit breakers, service discovery, sharding, rate limiting, consistent hashing, and auto-scaling, are the invisible machinery behind today's robust software. These aren't just interview topics, they're what make modern applications resilient and scalable. Each concept solves a specific problem, and together they form the backbone of reliable system design. Load balancing is the practice of distributing incoming traffic across multiple servers. Imagine a load balancer sitting between users and your application servers, ensuring that no single server gets overwhelmed. If one machine crashes, the load balancer reroutes traffic to healthy servers, keeping the application available and responsive. This approach allows you to scale horizontally by adding more servers, rather than relying on one powerful machine. Algorithms like round-robin or least connections help decide where each request should go, making traffic manageable and improving both performance and reliability. Hashing is one of the simplest yet most powerful ways to boost performance. Instead of fetching the same data from a database or calculating results repeatedly, a cache stores frequently accessed information in fast memory. When a user requests the same data again, the system serves it instantly from the cache, reducing latency and backend load. For example, product details requested by thousands of users can be cached in Redis or Memcache. While caching makes systems faster, it also introduces challenges like stale data and cache invalidation. Used wisely, caching turns repeated work into instant responses. Content Delivery Network, or CDN, brings static content closer to users by storing assets on edge servers around the world. When someone loads an image or video, the CDN serves it from a nearby location, dramatically reducing latency. This means a user in India doesn't have to fetch images from a server in the US if a local CDN node has a copy. CDNs also reduce load on your origin servers, absorb traffic spikes, and help protect against certain abuses. For global applications, CDNs are a must-have for speed and reliability. Not every task needs to happen instantly. Message queues allow your system to handle work asynchronously. When a user uploads a file or places an order, the task can be placed in a queue and processed later by another component. This decouples producers from consumers, letting each work at its own pace. Message queues are perfect for background jobs, email sending, and long-running tasks. They absorb traffic spikes and improve reliability, as messages can be retried if a worker fails. With queues, sudden pressure becomes controlled processing. Publish subscribe systems take messaging further by allowing multiple consumers to react to the same event. When an event occurs, like an order being placed, the producer publishes it, and various services such as payment, inventory, and notifications respond independently. This pattern lets systems evolve without tight coupling, making it easy to add new consumers without changing the producer. Publish subscribe is common in event-driven architectures, microservices, and real-time analytics, shifting the focus from direct calls to flexible event flows. API Gateway acts as the single front door to your backend. Instead of clients calling many services directly, they interact with the gateway, which handles routing, authentication, rate limiting, and more. This simplifies the client experience and centralizes security and traffic policies. Especially in microservice architectures, the API gateway hides internal complexity and provides a stable interface. However, it must be designed carefully as it becomes a critical component. Any issues here can affect the entire system. Circuit breaker protects your system from repeatedly calling failing dependencies. In distributed systems, if a downstream service fails, the upstream service might keep retrying, making things worse. The circuit breaker monitors failure rates, and if they exceed a threshold, it opens the circuit and temporarily stops calls to the failing service. This prevents cascading failures and allows the system to recover gracefully. After a while, it can test the dependency again and close the circuit if things improve. Sometimes, resilience means knowing when to stop trying. Modern distributed systems, service instances are constantly changing. Containers restart, pods move, and auto-scaling adds or removes instances. Hard-coding service addresses doesn't work in this environment. Service discovery automatically tracks available service instances, so when one service needs another, it asks the discovery system for a healthy instance. This keeps systems dynamic and resilient, allowing infrastructure to change without breaking communication. Service discovery is essential in Kubernetes, service meshes, and cloud-native platforms. As your data grows, a single database may not be able to handle all reads and writes efficiently. Sharding splits your data across multiple database nodes, distributing storage and workload. For example, users might be divided by ID ranges, with each shard handling a subset. Sharding allows your system to scale beyond the limits of a single node, but it introduces complexity. Choosing the right shard key is critical, and cross-shard queries can be challenging. Still, for large systems, sharding is often necessary for growth. Rate limiting protects your system from abuse and overload by controlling how many requests a client can make in a given time window. For example, an API might allow 100 requests per minute per user. If a user exceeds this, the system returns an error. Rate limiting ensures fair resource usage, prevents brute force attacks, and maintains predictable performance. It's a vital security tool for login endpoints, payment APIs, and public services, helping keep your infrastructure stable and secure. Persistent hashing is a technique for distributing data across nodes with minimal disruption when nodes are added or removed. In a simple hashing system, adding a new node can require remapping most keys, causing massive data movement. Consistent hashing solves this by placing nodes and keys on a logical ring, so only a small portion of keys move when the system changes. This makes scaling distributed caches and databases much smoother, allowing your system to grow without constant reshuffling. Autoscaling lets your infrastructure automatically adjust capacity based on demand. When traffic spikes, the system adds more servers. When demand drops, it scales back down. This keeps performance high while controlling costs. Autoscaling is often based on metrics like CPU usage or request count and works best with stateless applications and reliable health checks. While it doesn't solve all architecture problems, autoscaling gives your system the elasticity to handle real-world traffic without manual intervention. Each of these 12 concepts is powerful on its own, but real-world systems combine them for maximum resilience. A user request might first hit a CDN for static content, then go through an API gateway which applies rate limiting and routes traffic to a load balancer. The load balancer sends the request to a healthy service instance, discovered via service discovery. The service may check the cache, read from a sharded database, or trigger background work through a queue. If a dependency fails, a circuit breaker prevents cascading issues. If traffic surges, auto-scaling adds more resources. Consistent hashing helps distribute data efficiently. This interplay is what keeps modern systems robust and responsive. Understanding these concepts changes how you approach system design. You stop seeing backends as simple request handlers and start viewing them as living systems under constant pressure. You plan for traffic distribution before overload happens, implement caching before databases slow down, and set up queues before slow work blocks users. Rate limits and circuit breakers become proactive tools, not afterthoughts. This mindset shift is what defines architectural maturity, anticipating problems and designing for resilience from the start. Let's take a closer look at load balancing in real systems. Load balancers use algorithms like round-robin, least connections, or weighted routing to distribute requests. This ensures that no single server becomes a bottleneck. If a server fails, the load balancer detects it and reroutes traffic to healthy servers, maintaining uptime. Load balancing is essential for horizontal scaling, allowing you to add servers as your user base grows. Without it, scaling becomes fragile and unreliable. Hashing isn't just about storing data, it's about choosing the right strategy. You might use in-memory caches like Redis for fast access or CDN caches for static assets. Application-level caches can store computed results while database caches reduce query load. Each approach has trade-offs, especially around cache invalidation and data freshness. The key is to balance speed with accuracy, ensuring users get fast responses without outdated information. CDNs work by distributing static content to edge servers worldwide. When a user requests a file, the CDN checks if it's available locally. If not, it fetches it from the origin server and caches it for future requests. This process reduces latency and ensures users everywhere experience fast load times. CDNs also help absorb traffic spikes, making your application more resilient to sudden surges in demand. Message queues are invaluable for handling background jobs and asynchronous workflows. For example, when a user uploads a file, the upload service can place a message in a queue. A separate worker then processes the file, sends notifications, or updates records. This decoupling means your main application stays responsive even during heavy workloads. Queues also provide reliability, as failed tasks can be retried without losing data. Microservice architectures, publish-subscribe systems enable services to communicate through events. For instance, when an order is placed, the order service publishes an event. Payment, inventory, and notification services subscribe to this event and react independently. This approach allows you to add new services or features without modifying existing code, making your architecture more flexible and scalable. API gateways offer more than just routing. They handle authentication, authorization, request transformation, logging, and sometimes even response aggregation. By centralizing these concerns, gateways simplify client development and enforce consistent policies across your backend. However, because all traffic flows through the gateway, it must be highly available and performant to avoid becoming a single point of failure. Circuit breakers operate in three states: closed, open, and half open. In the closed state, requests flow normally. If failure spike, the breaker opens, blocking further requests to the failing service. After a timeout, it enters half open, allowing a few test requests. If they succeed, the circuit closes. If not, it stays open. This mechanism prevents your system from being dragged down by persistent failures and helps it recover gracefully. Kubernetes and other cloud-native platforms rely heavily on service discovery. As containers and pods are created or destroyed, the discovery system keeps track of healthy instances. When a service needs to communicate with another, it queries the discovery system for available endpoints. This dynamic approach allows your infrastructure to scale and adapt without manual intervention, ensuring reliable connections even as the environment changes. While sharding enables your database to scale, it comes with challenges. Choosing the right shard key is crucial. If it's not well balanced, some shards may become overloaded while others are underused. Cross-shard queries can be complex, requiring coordination across multiple nodes. Despite these hurdles, sharding is often necessary for very large systems, allowing them to handle massive amounts of data efficiently. Implementing rate limiting involves more than just setting a cap on requests. You can use fixed windows, sliding windows, or token bucket algorithms to control access. The goal is to ensure fairness and protect your backend from abuse or accidental overload. Rate limiting is especially important for public APIs, login endpoints, and payment systems, where security and stability are paramount. Consistent hashing is widely used in distributed caches like memcached or Redis clusters. When you add or remove cache nodes, only a small subset of keys need to be moved, minimizing disruption. This approach keeps your cache efficient and scalable, even as your infrastructure changes. Consistent hashing is a subtle but powerful tool for maintaining performance in distributed systems. Auto-scaling decisions are based on real-time metrics like CPU usage, memory consumption, request count, or queue depth. By monitoring these signals, your system can automatically add or remove resources as needed. This ensures you have enough capacity during peak times and save costs during low usage. Properly tuned auto-scaling policies are key to maintaining both performance and efficiency. Imagine a user request journey. It first hits a CDN for static assets, then passes through an API gateway which applies rate limiting and routes to a load balancer. The load balancer directs traffic to a healthy instance, discovered via service discovery. The service checks the cache, reads from a sharded database if needed, and may trigger background work via message queue. If a dependency fails, a circuit breaker steps in. If traffic spikes, auto-scaling adds more servers. Consistent hashing ensures distributed data stays balanced. This orchestration is what makes modern systems resilient. Learning these architecture concepts is a key step in evolving from a developer to a system designer. You begin to anticipate challenges before they arise, thinking about load balancing before servers overload, caching before databases slow, and circuit breakers before failures cascade. This proactive mindset is what sets great architects apart, enabling them to build systems that are not just functional, but resilient and scalable. Load balancers use various algorithms to distribute traffic. Round robin sends requests in order, least connections sends to the server with the fewest active connections, and weighted routing considers server capacity. Each algorithm has its strengths and is chosen based on the system's needs. The goal is always to maximize efficiency and prevent any single server from becoming a bottleneck. One of the hardest problems in caching is invalidation, deciding when to remove or update cached data. If data changes but the cache isn't updated, users may see stale information. Strategies like time-to-live (TTL), manual invalidation, or event-driven updates help keep caches accurate. Balancing freshness and performance is key to effective caching. Beyond performance, CDNs also enhance security. They can absorb distributed denial-of-service (DDoS) attacks, block malicious traffic, and hide your origin servers from direct exposure. By acting as a shield, CDNs help protect your infrastructure while delivering content quickly to users worldwide. Message queues improve system reliability by ensuring that tasks aren't lost if a worker fails. Messages can be retried or moved to a dead letter queue for later analysis. This guarantees that important work is not missed, even during failures or restarts, making your system more robust and fault-tolerant. Event-driven architectures, powered by publish-subscribe systems, allow you to add new features or services without disrupting existing ones. For example, you can introduce a new analytics service that subscribes to order events, gaining insights without changing the order service itself. This flexibility accelerates innovation and reduces risk. API gateways are a central point for enforcing security policies. They can manage authentication, authorization, input validation, and even threat detection. By consolidating these controls, you reduce the risk of vulnerabilities and ensure consistent protection across all backend services. When a circuit breaker opens, your system can use fallback strategies such as returning cached data or a default response. This ensures users still get a response even if it's not the latest data. Fallbacks help maintain user experience during partial outages and give your system time to recover. Service discovery systems often include health checks to ensure only healthy instances are returned to clients. This prevents requests from being sent to failing or overloaded services, improving reliability and reducing downtime. Automated health checks are a cornerstone of resilient, self-healing architectures. Sharding isn't just about storing more data, it also enables higher write throughput. By distributing writes across multiple shards, you avoid bottlenecks and allow your system to handle more concurrent operations. This is especially important for applications with heavy write loads like social networks or financial systems. Rate limiting is a powerful security tool. By capping the number of requests, you can prevent brute force attacks on login endpoints, limit scraping of public data, and protect sensitive APIs. Well-implemented rate limiting ensures your system remains stable and secure, even under attack. Consistent hashing isn't limited to caches, it's also used in distributed storage systems. By minimizing data movement when nodes change, it keeps storage balanced and efficient. This approach is vital for large-scale databases and file systems that need to scale seamlessly as demand grows. To get the most from auto-scaling, ensure your applications are stateless, health checks are reliable, and scaling policies are fine-tuned. Monitor your metrics and adjust thresholds as needed. Auto-scaling is not a silver bullet, but with the right setup, it provides the elasticity needed to handle real-world traffic patterns efficiently. Modern software architecture is not about choosing one pattern but about combining many. Each concept, load balancing, caching, sharding, and more solves a specific challenge. Together, they create systems that are fast, reliable, and ready for scale. The real skill lies in knowing when and how to apply each pattern for your unique needs. As you master these architectural concepts, your mindset shifts. You start thinking about resilience, scalability, and maintainability from the very beginning. You anticipate problems and design solutions before they impact users. This proactive approach is what sets apart great developers and system designers in today's fast-paced tech world. Great developers do more than write code that works, they build systems that survive. Load balancing keeps traffic under control, caching makes responses fast, CDNs reduce global latency, and queues decouple work. API gateways simplify access, circuit breakers prevent cascading failures, and service discovery keeps dynamic systems connected. Sharding, rate limiting, consistent hashing, and auto-scaling all play their part. Together, these concepts form the foundation of modern software architecture. If you want to grow from developer to system designer, learn these patterns deeply, because at scale, software is about resilience.